the measured cosmos. The night sky appears silent, but it is filled with time. Every point of light, every faint shimmer, reaching your eyes, began its journey long before human beings existed. Some of those photons have travelled for billions of years across the expanding fabric of space, crossing regions that no human ship will ever reach. When you look upward, you are not seeing distance, you are seeing the past. Astronomers call this sphere of everything we can observe the observable universe. It is not the whole cosmos, only the part whose light has had time to reach us since the Big Bang, 13.8 billion years ago. But because space itself has stretched while that light was on its way, the true diameter of the observable universe is about 93 billion light-years. The edge of what we can see lies roughly 46.5 billion light-years in every direction. This number is staggering, but it's not guessed, it's measured. It comes from the combination of deep sky surveys, cosmological models, and a constant first discovered by Edwin Hubble in 1929. Hubble found that distant galaxies are receding from us. Their light stretched to longer, redder wavelengths. The greater the distance, the faster the recession. From this, he derived the rate of expansion, the Hubble constant, which today modern satellites like Planck and Hubble Space Telescope have refined to a value between 67 and 74 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, galaxies are receding 67 to 74 kilometers per second faster. When Hubble made his discovery, the universe was thought to be static and eternal. His measurements shattered that illusion. The cosmos was expanding, implying that in the distant past it was smaller, hotter, and denser. A realization that became the foundation of the Big Bang theory. The expansion is not an explosion into empty space. It is space itself stretching. Galaxies are not moving through space like shrapnel from a blast. They are carried apart by the growth of space-time itself. The light from those galaxies encodes this expansion. Its redshift acts like a clock, allowing astronomers to reconstruct the universe's history. Our view extends outward through this ancient light, layer by layer. The deepest observations by telescopes such as Hubble and James Webb reveal galaxies so remote that their light began its journey when the universe was less than 1 billion years old. Counting them, extrapolating from tiny visible regions like the Hubble Ultra Deep Field, astronomers estimate that there are about 2 trillion galaxies within the observable universe. Each of those galaxies contains hundreds of billions of stars and likely even more planets. Beyond those galaxies lies not darkness, but the faint uniform glow of the cosmic microwave. Background: the oldest light we can see, a relic from a time before stars, discovered accidentally in 1964 by Arno Penzias and Robert Wilson. This radiation is a snapshot of the universe when it was just 380,000 years old. It fills all of space at a temperature of 2.725 Kelvin, only a few degrees above absolute zero. The small variations in its temperature measured later with the COBE satellite in 1989, WMAP in 2003, and Planck between 2013 and 2018 reveal the seeds of cosmic structure, the tiny density ripples that would one day grow into galaxies and clusters. The observable universe is therefore not a physical edge or a wall, but a horizon of time. Beyond it, light has simply not yet arrived. It is a limit imposed by the finite speed of light, 299,792 kilometers per second, and the finite age of the cosmos. Every year that passes, the observable universe grows by about 1 light-year in radius, because new light from more distant regions finally reaches us. Yet paradoxically, because space continues to expand, the galaxies that emitted that light may now lie far beyond our reach. When we measure the sky, we measure not just where things are, but when. The cosmic map is not drawn on distance alone, it is drawn on time's expanding canvas. The nearest stars shine from the past of a few years, the most distant quasars from a past older than the Milky Way itself. We are surrounded by concentric shells of history, each layer a record of how the universe once was. Everything we know, every atom, every law, every measurement comes from within this cosmic bubble. It is our visible domain, but perhaps only a small island in an unbounded ocean. To grasp what might lie beyond, we first must understand the boundaries that define what we can see. Horizons in an expanding universe. The universe does not end where our vision fades. What we call the edge is not a physical boundary, but a limit to what light has had time to tell us. Like the surface of the sea glimpsed from a ship, it marks the boundary of observation, not of existence. To understand that boundary, we must first understand cosmic horizons. There is more than one. The particle horizon marks the greatest distance from which light could have travelled to us. Since the beginning of time, our true observational limit. The event horizon, on the other hand, defines how far into the future we can ever hope to see or influence. Beyond it, light emitted today will never reach us, no matter how long we wait. These two horizons, the limit of what we can see and the limit of what we can ever see together, shape our cosmic perspective. When you gaze across the night sky, the farthest light you see comes from a time about 13.8 billion years after the beginning. Yet because of cosmic expansion, that light was emitted from regions now 46.5 billion light years away. The light's journey was a conversation between time and the stretching fabric of space, a dialogue recorded in its redshift. At that farthest visible boundary, we encounter the cosmic microwave background, or CMB. It is the afterglow of the recombination epoch, when the universe was dense, hot plasma, and photons could not travel freely. Around 380,000 years after the Big Bang, the temperature fell below 3,000 Kelvin. Electrons and protons combined into neutral hydrogen, and light was suddenly free to move. That light, now stretched by expansion into microwaves, still fills the cosmos today, faint but omnipresent. In 1964, when Arno Penzias and Robert Wilson first detected the CMB as an unexplained hiss, in their radio antenna, they had stumbled upon the edge of our visible universe. The discovery confirmed the Big Bang model and earned them the 1978 Nobel Prize in Physics. Later, missions COB in 1989, WMAP in 2003, and Planck between 2013 and 2018 mapped the CMB with ever finer precision. Planck's data showed that temperature variations across the sky were only about 1 part in 100,000, revealing how extraordinarily uniform the early universe was. Those tiny irregularities are the fingerprints of quantum fluctuations magnified during cosmic inflation, the brief, violent expansion that occurred around 10 to the power of negative 36 seconds after the Big Bang. In less than a trillionth of a second, the universe grew exponentially, smoothing its curvature and scattering those fluctuations across vast scales. Without them, there would be no galaxies, no stars, and no us. The Planck satellite also gave us something else, the most precise measurement of the universe's geometry. Its data show that the cosmos is spatially flat to within 0.1%. In cosmological terms, flat means that parallel lines remain parallel forever, that the universe's large-scale curvature is zero or nearly so. A perfectly flat universe could extend forever with no edges, no boundaries, and no center. But to an observer, even an infinite universe looks finite. Because light travels at a finite speed, we can only see as far as the universe's age allows. That limit is our particle horizon, roughly 46.5 billion light-years away. Beyond it, the universe continues, but its light has not yet arrived. There is another, more sobering horizon, the cosmic event horizon, a concept born from general relativity. In an accelerating universe driven by dark energy, space expands faster than light, can traverse it. This means there are galaxies whose light emitted today will never reach us. They exist forever beyond our communication, receding into eternal night. The current radius of that event horizon is about 16.5 billion light-years. To visualize this, imagine two distant galaxies at opposite ends of an expanding balloon. The surface of the balloon is space itself. As it inflates, the galaxies move apart, not by motion, through space, but by space stretching between them. At some distance, the rate of expansion outpaces the speed of light. Signals from one side can never reach the other, even though no law of physics is broken, because relativity forbids only motion through space faster than light, not the expansion of space itself. This is why the observable universe has a horizon, and why that horizon shifts with time. Every second, more distant light crosses the threshold and becomes visible to us, while at the same time, more distant regions cross another boundary to the event horizon and slip beyond reach. Forever, the visible cosmos grows, yet our ultimate reach contracts. From a practical standpoint, these horizons define the limits of cosmology. We cannot observe what lies beyond the CMB using light, because before recombination, the universe was opaque. It was filled with plasma, an ocean of free electrons scattering every photon. The CMB is therefore not just a limit of distance, but a limit of time. Beyond it lies the cosmic dark age, a period that can be explored only indirectly through theoretical models or through messengers that interact more weakly than light, neutrinos, or perhaps gravitational waves from the first instance of creation. In 2015, LIGO detected gravitational waves for the first time, ripples in space-time itself. In principle, a future observatory sensitive enough could detect primordial gravitational waves from the inflationary epoch, giving us a window into times far earlier than the CMB, into the first 10 to the power of negative 35 seconds of existence. But for now, those signals remain hidden in the noise, faint beyond our reach. The edge we see, then, is a mirage shaped by the laws of physics and the limitations of perception. It is not a wall surrounding the universe, but the outermost layer of what light allows us to witness. Beyond it, the cosmos continues, unseen but governed by the same laws that shape our own corner of space and time. If the universe is infinite, then every observer anywhere would see their own horizon, centered around themselves, each one their own observable bubble floating in an endless sea. There is no single edge, no border to reality, only countless horizons defined by time and light. And so, when we speak of the edge of the universe, we are really speaking of our edge of what the cosmos allows us in this moment to know. What the cosmic edge looks like. When we look far enough into space, we look into time so deep that galaxies vanish and the universe turns into a glowing fog. The light from that fog is the cosmic microwave background, the afterglow of creation itself. It is the oldest light we can ever hope to see the outer wall of. Our visible domain, this ancient radiation, does not shine like the stars. It is everywhere, equally bright in all directions, bathing the universe in a faint glow of microwaves at a temperature of 2.725 Kelvin. To human eyes it is invisible, but to radio receivers and satellites it is a perfect blackbody. Spectrum, the cooling ember of a once blinding fire. That fire was the early universe, a dense, hot plasma where energy and matter were inseparable. Roughly 380,000 years after the Big Bang, the expanding cosmos cooled enough for protons and electrons to combine into neutral hydrogen atoms. For the first time, light could move freely. The photons released in that moment have been travelling ever since, their wavelengths stretched 1,000-fold by the expansion of space. This event is called recombination, and its aftermath is what we observe today as the CMB. The snapshot it gives us is extraordinarily uniform. Across the sky, its temperature varies by no more than 1 part in 100,000. Those slight variations first mapped by Kobe in 1989, then with greater precision by WMAP in 2003 and Planck in 2013, 2018 are the fingerprints of quantum. Fluctuations amplified during cosmic inflation. In those tiny ripples of density, we see the seeds of everything. Every galaxy, every cluster, every star that would later shine. The CMB is, in a sense, a photograph of the universe as a newborn. When you look at its mottled pattern, you are looking at the earliest map of structure ever drawn. Bright regions mark slightly denser pockets where gravity would later pull matter together to form galaxies. Darker regions mark slightly thinner voids where matter would flow away from those faint imbalances. All the complexity of the universe unfolded. If you could travel to the edge of the observable universe, to the place where this light was, first released, you would not find a wall or a shell. You would find yourself surrounded by matter that has aged 13.8 billion years since that moment. The CMB is not an outer layer you could touch. It is the limit of what we can see from where we stand now. Every observer anywhere in the cosmos would see it surrounding them in all directions exactly as we do. The universe has no center. Every point is the center of its own visible sphere. What does the edge look like in human terms? It looks like an ocean of microwaves, each photon whispering a story from an age before stars existed. In 1992, Cobb's FIRES instrument confirmed that this light had an almost perfect black-body curve, evidence that the early universe was once in thermal equilibrium at about 3000 Kelvin. At that time, the universe was only about 100,000 light-years across, and its average density was about 1 billion kilograms per cubic meter, a trillion times denser than it is today. Over billions of years, that dense plasma expanded and cooled. Space grew by a factor of roughly 1,100 since recombination, stretching those 3000 Kelvin photons into microwaves of a few millimeters in wavelength. The cosmic expansion is written into every one of those photons, each one a stretched thread connecting the present to the dawn of time. The CMB also holds subtle clues about the geometry of space itself. By measuring the apparent size of the temperature fluctuations on the sky, scientists can test whether the universe is flat, open, or closed. A flat universe, like an infinite sheet, would produce fluctuation patterns of a specific angular size, about 1 degree on the sky. Planck's data confirmed precisely that, implying that the universe's curvature is so close to zero that if it is curved at all, its radius of curvature must be at least 250 times larger than the observable universe. In other words, space may be vast beyond imagining, effectively infinite to us. The CMB also reveals that the universe's composition is not what common sense would expect. Only about 4.9% of its total energy content is ordinary matter, the atoms that make stars, planets, and life. About 26.8% is dark matter, an invisible mass that tugs gravitationally but does not emit light. The remaining 68.3% is dark energy, a mysterious pressure that drives the universe's accelerating expansion. These numbers are not guesses. They come from fitting Planck's CMB data to the equations of general relativity and the LLCDM, model the standard cosmological framework. So, when we say we see the edge of the universe, what we truly see is the first moment light could move freely. It is a picture frozen in time, not a border in space. Beyond that, the universe existed dense, opaque, unknowable to photons. To peer deeper, we must look with different messengers. Cosmologists are now searching for the cosmic neutrino background predicted to have formed about 1 second after the Big Bang, when the universe was still 1 billion degrees hot. These relic neutrinos would fill space even more uniformly than the CMB, but because they interact so weakly, detecting them directly remains beyond current technology. Similarly, primordial gravitational waves ripples in space-time from the first instance of inflation could reveal what happened even earlier, in the first 10 to the power of negative 35 seconds. If we ever detect them, we would glimpse the universe before light itself existed. For now, the CMB remains our ultimate wall of sight, the luminous fossil of creation. It is the universe's first memory and our last visible frontier. Every image we have of the cosmos, every deep field, every map of galaxies and clusters, floats within this spherical boundary. The edge of the visible universe is not the end of space, but the beginning of time, the place where our story first becomes visible. How space itself grows. It is easy to imagine the universe expanding, like an explosion matter flung outward from some central point into pre-existing emptiness. But that image is wrong. The expansion of the universe has no center, no outside, no place where it began. It is not matter moving through space. It is space itself growing, carrying matter along with it, like raisins embedded in rising dough. This idea first appeared in the mathematics of Albert Einstein's general theory of relativity, published in 1915. When Einstein applied his equations to the entire cosmos, he found that space could not remain static. Gravity would make it contract. To hold the universe still, he added a cosmological constant, a kind of repulsive term to counterbalance gravity. But when Edwin Hubble discovered cosmic expansion in 1929, Einstein called that constant his greatest mistake. The universe did not need to be propped up. It was already expanding on its own. The speed of this expansion is set by the Hubble parameter, which changes over time. Today, its value is about 70 kilometers per second per megaparsec, meaning that two galaxies, separated by 3.26 million light-years, move away from each other about 70 kilometers per second faster for every additional megaparsec of distance. But in the early universe, that number was far higher. At first, expansion slowed because of gravity pulling matter together. Later, about 5 billion years ago, a mysterious force called dark energy began to dominate, causing the expansion to accelerate again. This discovery, made in 1998 through observations of distant Type Ia supernovae by two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, won the 2011 Nobel Prize in Physics for Perlmutter, Schmidt, and Rees. Yet the story of expansion begins long before that, according to modern cosmology, right after the Big Bang. The universe underwent a brief but extraordinary phase known as cosmic inflation. Proposed by Alan Guth in 1981, inflation solved several mysteries of the Big Bang model. Why the universe appears flat, why it looks the same in every direction, and why it contains so few magnetic monopoles, hypothetical relics that theory once predicted in abundance. Inflation suggests that in the first 10 to the power of negative 36 seconds after the Big Bang, the universe expanded exponentially, doubling in size again and again in a tiny fraction of a second. By the time inflation ended, it had grown from a quantum scale speck to something perhaps 10 to the power of 26 times larger, smoothing out curvature and distributing matter evenly. Tiny quantum fluctuations during that process became the seeds of all later structure, the faint ripples we now see imprinted on the cosmic microwave background. After inflation ended, the universe continued to expand more gently, filled with hot plasma on the next 380,000 years. As it cooled, light finally broke free, giving rise to the CMB. Then, after hundreds of millions of years, gravity gathered matter into the first stars, lighting up the cosmos. Those stars formed galaxies, which grouped into clusters, which spread across vast filaments. Spanning hundreds of millions of light-years, the cosmic web Expansion defines that web. Every megaparsec of space between clusters grows larger with time. But galaxies bound together by gravity, like those in our local group, including the Milky Way and Andromeda, remain together. Their gravity overwhelms expansion on small scales. That is why galaxies do not expand, and neither do solar systems or atoms or you. Expansion acts only on the grandest scales, in the space between galaxy clusters. One of the most misunderstood facts in cosmology is that expansion can make galaxies move away from us faster than the speed of light. This does not violate relativity, because relativity, it forbids faster than light motion through space, not faster than light separation caused by space. Expanding. A galaxy 15 billion light-years away recedes at about 1.1 times the speed of light. We can still see it today because the light it emitted long ago is only now arriving, but new light emitted now will never reach us. It is already beyond our event horizon. The mathematics of this process come from the Friedmann equations, derived independently by Alexander Friedmann in 1922 and Georges Lemaître in 1927. These equations describe how the universe's expansion rate depends on its energy, content matter, radiation, and dark energy, and its curvature. Observations show that the universe's density is remarkably close to the critical value that makes space flat, corresponding to a total energy density of about 9.5 times, 10 to the power of negative 27 kilograms per cubic meter, roughly 6 hydrogen atoms per cubic meter. Every point in the universe is expanding away from every other point, yet no point is the center. The observable universe is a sphere only from our perspective to someone in a galaxy billions of light years away. Their observable sphere would look the same. The expansion does not carry matter outward from a common origin, but stretches the entire fabric evenly. If the universe is infinite, it has always been infinite. Only the scale of everything within it changes. The rate of this expansion, known as the scale factor, has increased by about a factor of 1,100 since the time of recombination. Over cosmic time, the scale factor acts like the heartbeat of the universe, encoding its evolution in a single curve. By tracing it, cosmologists reconstruct the universe's history: radiation domination in the first 47,000 years, matter domination for the next several billion, and dark energy domination from roughly 5 billion years ago onward. The discovery of dark energy was a shock. It suggested that not only is the universe expanding, but that expansion is accelerating. If this continues indefinitely, galaxies will drift apart until, in the far future, every distant light fades beyond the event horizon. Billions of years from now, observers in the Milky Way, if any remain, will see only their own galaxy. The rest of the cosmos will have slipped forever beyond reach, leaving them alone in darkness, unaware of the vast universe that once surrounded them. Yet this acceleration may not be forever. Some theories suggest dark energy could change or fade. Others propose that expansion might reverse in a distant future big crunch. Still others predict a big rip where expansion eventually tears apart galaxies, stars, and even atoms. Each scenario depends on the nature of dark energy, a mystery we have only begun to explore. To measure it, astronomers use cosmic probes, supernovae, baryon acoustic oscillations, CMB, data, and gravitational lensing. Together, these observations form a coherent picture of an expanding universe governed by dark energy and cold dark matter, a model known as LCDM. It is the most successful description of the cosmos yet, accounting for everything from the birth of the CMB to the motion of galaxies billions of light years away. So when we say the universe is expanding, we mean that the very metric of space, the distance between any two unbound points, is increasing. Space is not empty, it is dynamic, elastic, capable of growth. The galaxies are beads on a stretching thread. Their recession is not flight but participation in a grand, continuous unfolding. The tapestry of the cosmos is still being woven. Every second, new space comes into being between the galaxies. Every photon traveling through that expanding fabric carries a record of its stretching, its wavelength lengthened by the growth of the universe itself. The night sky is full of this music of expansion, its rhythm written in the shifting colour of light. The question that follows is both simple and profound. If space can expand forever, does it go on without end? And if it does, how can it still have an edge we can see? Infinite space and its possible shapes. When you gaze into the night sky, it is natural to wonder, if the universe expands, what does it expand into? The answer is subtle and astonishing. Space does not expand into anything. It expands within itself. There is no outside, no border, no emptiness waiting to be filled. The universe contains all space, and space contains everything we know. From the measurements of the cosmic microwave background, we know that the universe is remarkably flat. In cosmology, flatness does not mean two-dimensional. It means that on the largest scales, parallel lines never meet, and the rules of Euclidean geometry hold true. The Planck mission in 2018 measured the spatial curvature of the universe, denoted omega, and found it to be 0.00007 plus or minus 0.0019, effectively zero. That result implies that the universe is either infinitely large or so vast that any curvature is too gentle to detect within our 3 billion light-year observational bubble. To picture this, imagine standing on the surface of Earth. The ground looks flat, though we know it curves gently beneath our feet. If you could walk far enough, you would eventually return to where you started. The same could be true of the universe. It might curve back on itself, like the three-dimensional analogue of a sphere. But if that curvature spans hundreds of trillions of light years, we would never know. To us, it would seem perfectly flat. Cosmologists have proposed several possible global topologies for space. One is a closed universe, shaped like a four-dimensional sphere, finite, but without boundaries, like the surface of a globe. Another is an open universe, with negative curvature, shaped like a saddle that extends forever in all directions. The third are best fit from current data is the flat universe, infinite and unbounded. But even a flat universe could still be finite in a topological sense. Space might wrap around itself, forming a shape called a three-torus. Imagine a cube whose opposite faces are connected so that travelling out one side brings you back through the other. In such a universe, you could, in principle, see multiple images of the same galaxy appearing at different points in the sky. There, light looping around the cosmos. The WMAP and Planck missions searched for this by looking for matched circles repeating, patterns in the CMB where the light from the same region might have travelled different routes to reach us. So far, no such pattern has been found, suggesting that if space does wrap around, its scale is far larger than our visible horizon. The implications are profound. If the universe is truly flat and infinite, then there are no edges, no centre, and no outside. The Big Bang was not an explosion from a point into emptiness. It happened everywhere at once, in every region of space, including the one you now occupy. Every observer in every galaxy sees themselves at the centre of expansion, because expansion happens between all points, simultaneously. An infinite cosmos raises strange consequences. In a space that extends without limit, every possible configuration of matter should occur somewhere. There would be another region of space, unimaginably far away, where the atoms of another person arranged themselves exactly as yours are now a cosmic doppelganger. The distances between such repetitions would be mind-bending. According to one estimate by cosmologist Max Tegmark, if the universe is infinite and random on large scales, the nearest identical copy of you might be about 10 to the power of 1029 meters, away a number so vast that it dwarfs even the concept of distance itself. Yet infinity may not be the only answer. Some models suggest that the universe could be closed, looping back on itself like a cosmic hypersphere. In this case, if you travelled far enough in one direction, you would eventually return to your starting point, though from a different epoch in time, in a closed universe. The total volume is finite, but without boundaries, there is no outside to fall off. Einstein himself considered this possibility in 1917, proposing a static, closed universe of finite size. Later, observations of expansion rendered that model obsolete, but the underlying geometry remains possible. A closed universe would eventually halt its expansion and recollapse in a big crunch. A flat or open universe, on the other hand, will expand forever. Today, with the dominance of dark energy, a closed model seems unlikely, but not ruled out. The BOSS survey, Baryon Oscillation Spectroscopic Survey, in 2014, and Planck's final data release in 2018 together suggest a curvature so small that if the universe is curved, its radius must be at least 250 times the radius of the observable universe. That means even if space does bend, the curvature would be imperceptible on any scale we could ever measure. But geometry alone does not settle the question. Space could be flat and infinite, or flat and finite but multiply connected. It could even have exotic shapes that defy simple visualization spaces that twist, fold, or link like knots in higher dimensions. The language of mathematics allows such forms. Whether nature uses them is still unknown. The observable universe gives us only one patch of this grand design, a single cosmic volume. We cannot see beyond our horizon, so we cannot know whether space continues forever or eventually closes upon itself. The question remains open not because it lacks answers, but because the answers lie beyond what light can bring us. And yet, even from this small vantage, we can infer something remarkable. The cosmos is larger, smoother, and more symmetrical than any ancient imagination ever dared to dream. It stretches beyond the reach of light, beyond the reach of even our equations, and yet it feels consistent, governed everywhere by the same physical laws. The universe may be infinite, but it is not chaotic. Its shape, whatever it truly is, obeys a deep coherence, a logic written into the fabric of existence. Whether space loops back on itself or extends endlessly, whether its curvature is positive, negative, or none at all, the laws of physics seem to apply equally in every corner. So when we speak of the universe's edge, we are really confronting the edge of knowledge. The cosmos may have no walls, no bounds, and no outside-only limits to our understanding. The geometry of reality stretches beyond what we can see, but within what we can imagine, beyond our bubble. The story of the cosmos may not end with our universe. The equations that describe the beginning of time do not forbid others, perhaps infinite others, each born with different laws, different histories, and different fates. The idea is no longer only a thought experiment, it is a mathematical consequence of theories that already explain the world we see. When Alan Guth proposed cosmic inflation in 1981, he solved several mysteries of the Big Bang. Why the universe looks the same in every direction, why it appears flat, and why it contains no relic magnetic monopoles. But his model also opened a door to something larger. Inflation, according to further work by André Linde, Paul Steinhardt, and others, may never end, everywhere at once. In the version known as eternal inflation, space is a restless, self-replicating field. Tiny regions of it stop inflating and cool, forming bubble universes like ours. But the space between those bubbles keeps inflating faster and faster, pushing them apart forever. Each bubble becomes its own universe, isolated by an ever-growing gulf of inflating space. The process never stops. New universes continue to appear endlessly, a cosmic foam of creation without limit. Our observable cosmos, everything within 46.5 billion light-years, would be only one bubble, among perhaps an infinite number, each with its own laws of physics. Inside one bubble, electrons might weigh what ours do. In another, they might not exist at all. The speed of light, the strength of gravity, the value of the cosmological constant all could differ from one universe to another. This is not fantasy. It follows naturally from the mathematics of inflation combined with quantum field theory. In quantum physics, energy fields fluctuate constantly, even in apparent emptiness. During inflation, such fluctuations can push regions of space to continue expanding while others stop. Each new bubble inherits a slightly different set of physical constants from the quantum fluctuations that birthed it. In 1983, André Linde formalized this as the chaotic inflation model, showing that once inflation begins, it never fully ends. Space as a whole becomes infinite and eternally producing new. Universe is a self-sustaining cosmic fractal. In this vision, our universe is not the product of a single beginning, but one blossom in an endless cosmic garden. Some cosmologists find this idea elegant. Others find it troubling, even unscientific. A universe we cannot observe, they argue, is not a subject of physics, but the multiverse emerges not from speculation but from equations that already explain what we can see. If inflation happened once, why should it not happen elsewhere? String theory, too, adds its own vastness to the picture. In the 1,990 seconds, physicists discovered that string theory, an attempt to unify all forces and particles into a single framework, allows an enormous number of possible solutions. The number is sometimes estimated at 10 to the power of 500, representing different ways the extra dimensions of space could curl and compactify. Each configuration would produce different physical constants, different particles, and perhaps entirely different kinds of physics. This vast collection is called the string landscape. In this view, eternal inflation populates the string landscape. Each bubble universe corresponds to a different vacuum state, a different point in that multidimensional space of possibilities. Some might be short-lived, collapsing in a flash. Others might expand forever, producing stars, galaxies, and life. Ours might simply be one of the rare universes where the physical constants allow complexity to emerge, a tiny habitable island in an infinite sea of sterile worlds. Even if we can never visit those other universes, there might be indirect clues, the boundaries between bubbles, if they ever collide, could leave scars in the cosmic microwave. Background, subtle circular patterns, or temperature anomalies. Teams studying data from WMAP and Planck have searched for such signs. A few regions, like the cold spot in the southern sky, have stirred speculation, though none are yet conclusive. If such evidence were ever found, it would mark one of the greatest discoveries in science, proof that our universe is not alone. There are other kinds of multiverse too, ideas born not of inflation but of quantum mechanics itself. In 1957, Hugh Everett III proposed the many worlds interpretation of quantum physics. In this view, the universe does not choose one outcome when a quantum event occurs. It realizes all outcomes, each in its own branching world. Every decision, every measurement, every flicker of possibility generates a new parallel reality. The many worlds interpretation is not the same as the cosmological multiverse, but the two are sometimes connected. In some formulations of quantum cosmology, the universe's wave function includes all possible histories, and in an inflationary background, each bubble could correspond to one of those histories becoming real. In Max Tegmark's classification, there are 4 levels of multiverse. Level I, regions beyond our observable horizon in the same physical space. Level 2, other bubble universes with different physical constants born from eternal inflation. Level 3, quantum many worlds, branching with every event. Level 4, universes governed by entirely different mathematical structures, universes, where the laws themselves differ. Each level extends the concept of reality a step further. None of them contradict what we already know. They simply push it to its logical extreme. Whether nature truly realizes any of these remains an open question. Even if the multiverse exists, it is unlikely we will ever contact another universe. The inflationary space between bubbles expands faster than light. Their boundaries recede eternally. But the idea changes how we think about our own existence. If there are countless universes, each with random laws, it may not be coincidence that we live in one that allows life. This is sometimes called the anthropic principle, not as a statement of purpose, but of probability. Life can only ask questions in places where the answers make it possible. In this grand view, Our universe is one note in a cosmic symphony, a single vibration in an infinite score. Each universe contributes to the total harmony of existence. Whether or not its melody ever reaches our ears, and yet from within our bubble, we can still read the echoes of that greater structure. The same mathematics that predicts a multiverse also gives us the patterns in the CMB, the distribution of galaxies, and the laws that govern matter and energy here at home. We may be unable to see beyond our cosmic horizon, but the horizon itself may be evidence that something larger continues beyond it. If inflation truly never ends, then creation itself is infinite. Space forever gives birth to space. Universes bloom and fade like sparks in an eternal storm, and our tiny island of stars is one spark among uncounted others, each carrying its own light into the endless dark, what we can never see. There are boundaries in nature that no telescope, no spacecraft, no imagination can cross. They are not walls of matter, but walls of principle, the unbreakable limit set by physics itself. When we peer into the darkness beyond the galaxies, we are already reaching the edge of knowable reality. The light we see from the most distant quasars began its journey more than 13 billion years ago, when the universe was young. Beyond that, there is only the faint afterglow of the cosmic microwave background, and beyond that, no light at all. The universe was opaque. Before 380,000 years after the Big Bang, a plasma so dense that photons could not travel. This is the cosmic photosphere, the surface of last scattering, beyond which light cannot carry information. Even if we built a telescope larger than the Earth, even if we waited for eternity, no, new photons from before that time would reach us. The light simply does not exist. To see earlier than that, we must imagine other messengers, particles and waves that interact more faintly with matter. One is the cosmic neutrino background, formed about 1 second after the Big Bang, when the universe cooled to around 10 billion Kelvin. Trillions of these neutrinos pass through every square centimetre of your body each second, remnants of the universe's first heartbeat. Detecting them directly is beyond our current reach, though experiments such as Ptolemy and Katrin may one day sense their faint fingerprints. Another messenger could be gravitational waves, ripples in the fabric of space-time itself. The LIGO and Virgo observatories first detected them in 2015, emitted by merging black holes a billion light-years away. But if we could detect gravitational waves at much lower frequencies, waves from the first fractions of a second after the Big Bang, we could see beyond the opaque plasma into the very birth of space and time. Projects like LISA, the laser, interferometer space antenna planned for the 2030 seconds may bring us closer to that goal. But even those breakthroughs would not reveal the entire cosmos. The greatest limit of all is the cosmic event horizon, the distance beyond which events today will never be observable. No matter how long we wait, because the expansion of the universe is accelerating, driven by dark energy. Galaxies beyond about 16.5 billion light-years are receding faster than light. The light they emit now will never reach us. This is not a technological problem. It is a structural one, a consequence of Einstein's general relativity. Space itself is stretching faster than light can cross it. As time passes, more galaxies will cross that horizon and vanish from view. In the far future, perhaps 100 billion years from Now, observers in the Milky Way, if any remain, will see only the stars of their own galaxy. All others will have faded beyond detection, their light stretched into invisibility by cosmic expansion. This future was first realized in the late 1990 seconds after the discovery of the universe's accelerating expansion. Astronomers like Adam Rees, Brian Schmidt, and Saul Perlmutter realized that dark energy would eventually isolate every galaxy, erasing the cosmic web from future skies. The night will grow emptier, not because stars die, but because the universe itself hides them. Even now, the light we see from the most distant galaxies carries both revelation and loss. It shows us how they once were, not how they are. Some may no longer exist. The light that reaches us tonight left when Earth itself was forming more than 4.5 billion years ago. Every telescope is a time machine, but only one that looks backward. There is no way to see the present of the distant cosmos, only its memory. And there are limits closer to home. Within black holes, gravity becomes so intense that not even light can escape. The boundary where escape becomes impossible is the event horizon, a perfect analogue to the cosmic one. Beyond it, the interior is forever hidden, its contents unknowable to the outside world. In the same way, the universe itself has an event horizon, a boundary in time and space, beyond which events are cut off from us forever. Information cannot travel faster than light, and light cannot outrun the expansion of space. This dual constraint defines the ultimate edge of observation. We can calculate what lies beyond, infer it from physics, but never see it. In this sense, the universe itself has regions permanently beyond communication, cosmic exile zones that no message, no signal, no light will ever reach. The James Webb Space Telescope, launched in 2021, has pushed our sight deeper into the past than ever before. It has imaged galaxies from less than 400 million years after the Big Bang, glowing red with ancient light. But even Webb is bounded by the horizon of time. No mirror, no lens can reach further, because there is no earlier light to gather. Beyond that, we rely on equations on the extrapolation of general relativity, quantum mechanics, and the cosmological principle. These tools let us infer conditions that can never be directly observed: the temperature, density, and curvature of the early universe, the behavior of inflation, the geometry of space-time beyond our bubble. But they are inferences, not images. They are the mathematics of imagination. Physicists sometimes speak of the cosmic light cone, the region of space-time that can influence or be influenced by us. Everything we will ever see or touch lies inside that cone. Everything outside is beyond forever. The edges of the light cone expand as time passes, but only to a limit. The event horizon defines the outermost boundary of causality. The cosmos continues beyond it, but for us, it is as if it were never there. This horizon defines the boundary between science and metaphysics. What lies beyond can be modelled but not measured. We can say what might exist but never verify it. And that is not failure. It is the structure of reality itself. The laws that make knowledge possible also set its limits. So when we speak of the edge of the universe, we are describing a frontier not of matter, but of information, the furthest place where the conversation between light and time can still reach us. Beyond that, silence begins. Not the silence of absence, but the silence of inaccessibility. And yet, that silence is not emptiness. Beyond every horizon lies more universe unseen, untouched, but as real as our own. The limit is not in the cosmos, it is in us. Cycles, folds, and alternate cosmologies. The story of the universe is often told as a single arc, a beginning, an expansion, and an eventual end. But what if the cosmos has no true beginning or end at all? What if creation and destruction are not opposites, but stages in an eternal rhythm? The standard cosmological model, known as LCDM, describes an expanding universe that began 13.8 billion years ago and will continue expanding indefinitely, driven by dark energy. But LCDM is not the only possible story written in the equations of general relativity. Over the past century, physicists have imagined many others, each one a variation on the same theme. How space, time, and energy dance together on the largest scale. In 1922, Alexander Friedmann derived solutions to Einstein's field equations showing that the universe could expand, contract, or oscillate depending on its total density. A dense universe might one day slow its expansion, halt, and collapse back inward, a closed universe ending in a big crunch. A less dense one might expand forever, an open universe, fading into a cold, empty eternity. For decades, cosmologists debated which fate awaited us. Then, in 1998, observations of distant supernovae revealed that expansion is not slowing, but accelerating. Dark energy had entered the story, and with it, a new set of possibilities. If dark energy remains constant, the simplest case, the universe will continue to expand exponentially. Galaxies will drift beyond sight. Stars will burn out. Black holes will evaporate. In about 10 to the power of 100 years, the cosmos will approach heat death, a state of near-perfect entropy where nothing more can happen. This is the Big Freeze, a universe not destroyed, but exhausted. If dark energy grows stronger over time, however, the outcome could be far more dramatic. In a model proposed by Robert Caldwell and colleagues in 2003, known as the Big Rip, the acceleration becomes so extreme that it eventually overcomes all other forces. First, galaxy. Clusters are torn apart. Then, galaxies themselves disintegrate. Stars and planets are ripped from their orbits. Finally, even atoms are pulled apart as the expansion rate exceeds the forces that bind them. If this model is correct, the end would come roughly 22 billion years from now, a universe, unraveling into pure, stretched vacuum. But not all cosmologists accept a final ending. Some suggest the universe may be cyclic, reborn endlessly in a sequence of expansions and contractions. This idea has deep roots. Ancient Hindu cosmology described a universe that breathes in and out across infinite ages. In modern physics, versions of this concept appear in the ekpyrotic and cyclic universe models proposed by Paul Steinhardt and Neil Turok in the early 2000s. In the ekpyrotic scenario, our universe is a three-dimensional brain, a membrane-like structure floating in a higher dimensional space. Occasionally, it collides with another brain, releasing immense energy that appears from within, as a Big Bang. After expansion, cooling, and eventual recollapse, the cycle repeats. Each collision begins a new universe, seeded with the structure of the last. In this view, the Big Bang was not the first moment of time, but the latest in an eternal sequence of cosmic bounces. Another cyclic concept comes from Sir Roger Penrose's conformal cyclic cosmology, CCC, proposed in 2010. Penrose argues that, in the far future, when all matter decays and black holes evaporate, the universe will become a smooth, empty sea of radiation. In such a state, without massive particles to define scale, time, and distance, lose their meaning. In that limit, the geometry of an infinite, cold universe becomes mathematically identical to that of an infinitesimal, hot one. The end of one universe thus becomes indistinguishable from the beginning of the next. Penrose even claimed to find possible evidence of this idea in concentric circles in the CMB, Hawking points, though the data remain controversial. Other speculative models propose alternate shapes of time itself. In loop quantum cosmology, space-time is quantized, built from discrete units. Instead of a singular Big Bang, the universe bounces when density reaches a critical maximum, avoiding the infinite curvature of A, singularity. This quantum bounce replaces the beginning with a transition, a bridge from a prior contracting universe to our expanding one. And then there are models that add dimensions beyond our own. In brane-world cosmologies, inspired by string theory, our entire universe might be a three-dimensional surface embedded in a higher dimensional bulk. Gravity could leak between branes, explaining why it is weaker than the other fundamental forces. Collisions or interactions between branes could ignite new universes, or even alter the expansion of our own. Some theories imagine universes budding off from black holes themselves, each singularity, the seed of a new cosmos, born on the other side of an event horizon. In this picture, every black hole in our universe could contain another universe within it, smaller from our perspective, but vast to the inhabitants inside. And our own Big Bang might have been the interior of a black hole that formed in a previous universe. Though these ideas stretch imagination, they all emerge from the same drive: to reconcile what we know with what might lie beyond the limits of observation. Each model respects Einstein's equations, but explores different ways those equations might unfold under extreme conditions. We have not yet measured which, if any, of these visions is true. Current data favor an accelerating, flat universe consistent with LCDM1 that expands forever, growing colder and emptier. But the door remains open. The universe's future depends on the nature of dark energy, and we still do not know what dark energy is. It could decay, reverse sign, or fluctuate. The cosmos may have surprises still to come. The one constant in all these models is that the universe evolves. Whether in one great expansion or an infinite series of rebirths, time itself is dynamic A, dimension that grows, curves, and perhaps folds back on itself. The cosmos is not a static object, but a process, and that process may have no true beginning or end. To study these possibilities is to confront the limits not only of measurement, but of imagination. The mathematics of general relativity and quantum theory allow for realities far stranger than intuition can follow. But even in their diversity, these models share one truth. The universe is not fragile. It endures, transforms, and renews in forms we are only beginning to guess. Perhaps the ultimate shape of time is not a line, but a circle or a spiral, forever turning upon itself. In that endless motion, beginnings and endings lose their meaning. There is only the rhythm of creation, the pulse of being that has no edge, no origin, and no final. Silence. Structure on the grandest scale. When you step back far enough beyond the stars, beyond the galaxies, beyond even clusters of galaxies, the universe begins to reveal a deeper pattern. It is not a random scattering of matter, but an intricate structure, a vast, three-dimensional web of filaments and voids spanning billions of light years. This is the cosmic web, the largest structure ever observed. It is the architecture of the universe itself, drawn by gravity over 13.8 billion years from the faintest ripples in the early cosmos. If you could see it all at once, if your eyes could trace the positions of 2 trillion galaxies across 93 billion light years, it would resemble a neural network or the veins of a living organism. The galaxies are not spread evenly through space. They flow along filaments, clustering at their intersections in immense superclusters. Between them lie enormous voids, some hundreds of millions of light years across, nearly empty of matter. The pattern was first hinted at in the 1,970 seconds and 80 seconds, when redshift surveys began mapping galaxies in 3 dimensions. Astronomers like Margaret Geller and John Huchra revealed a universe that looked like soap bubbles frozen in time. The famous CFA 2 Great Wall, discovered in 1989, stretched nearly 500 million light-years across. Since then, surveys like the Sloan Digital Sky Survey, SDSS, 2DF Galaxy Redshift Survey, and, most recently, DESI, the Dark Energy Spectroscopic Instrument, have charted millions of galaxies, transforming our view of energy, the cosmic landscape. From this cartography of the cosmos emerged the picture we now know. Galaxies form along filaments of dark matter, the invisible framework that makes up about 85% of all matter in the universe. These filaments are the skeleton upon which luminous matter, gas, stars, galaxies has gathered. The web formed as gravity amplified the tiny density fluctuations imprinted in the cosmic microwave background. Over billions of years, the slightly denser regions drew in more matter, while emptier regions became the cosmic voids. At the junctions of these filaments, gravity built vast structures known as superclusters. The Virgo supercluster, which includes our Milky Way, is just one branch of an even grander structure, the Laniakea supercluster, identified in 2014 by Brent Tully and colleagues. Laniakea Hawaiian, for immense heaven, spans over 500 million light-years and contains about 100,000 galaxies. But even it is not alone. Beyond lies the Hercules Corona Borealis Great Wall, discovered in 2013, the largest known structure in the observable universe, stretching an estimated 10 billion light-years end to end. To visualize these scales is almost impossible. If the Milky Way were reduced to a grain of sand, the Virgo cluster would be a handful of pebbles. The Laniakea supercluster would fill a small mountain range. The cosmic web would sprawl across continents, its filaments connecting mountain to mountain, separated by empty. Valleys representing the cosmic voids, regions where the density of matter is less than 1/10 the cosmic average. And yet, even this immense structure is not static. The filaments are not cosmic highways frozen. In place, they are rivers of time. Dark matter continues to flow along them, feeding the clusters. At their intersections, simulations like the Millennium Simulation 2005 and the illustrious TNG project have shown this process in detail, evolving billions of particles under gravity to recreate the universe's structure as we observe it. These digital universes reproduce, almost perfectly, the patterns seen by our telescopes, the same filaments, voids, and clusters, each grown from the quantum ripples of the early universe. But dark matter, the main sculptor of this architecture, remains unseen. We infer its presence from gravity's fingerprints, the way galaxies rotate too fast to be held together by visible matter. Alone, the way light bends around massive clusters in patterns that reveal invisible mass, phenomenon known as gravitational lensing. In 2006, the Bullet cluster provided one of the clearest proofs: two colliding clusters whose ordinary matter, seen in X-rays, was offset from the true center of gravity traced by lensing. Something unseen was carrying most of the mass. That unseen matter forms a cosmic scaffold extending across space. On this invisible lattice, gas collects, cools, and condenses into galaxies where stars ignite and planets form. Without dark matter, there would be no structure at all, no galaxies, no stars, no us. The universe would be a thin, featureless fog of hydrogen expanding forever. The largest voids, like the Bootes void, discovered in 1981 by Robert Kirshner and colleagues, span nearly 330 million light-years. These vast hollows are so empty that a single galaxy may drift in the middle, isolated from all others. If you lived in such a galaxy, you would see almost no external galaxies in your sky, only a few faint smudges at the horizon of sight. 2. Those hypothetical observers, the universe would seem utterly lonely, even though they, too, are connected to the same invisible web. The structure of the cosmic web is not random. It encodes the physics of the early universe. The separation between filaments, the size of voids, and the clustering of galaxies all carry the imprint of baryon acoustic oscillations, BAO, sound waves that rippled through the hot plasma of the early cosmos before recombination. Those ripples left a characteristic scale about 500 million light-years that still shapes the distribution of galaxies today. By measuring that scale at different epochs, astronomers can trace how the universe's expansion has changed over time. Each observation adds a new layer to the grand map, and the map keeps growing. The Euclid mission, launched 2023, and Nancy Grace Roman Space Telescope, set for 2027, are designed to chart billions of galaxies, extending our cosmic map to the edge of the visible. In their data, the filaments will stretch across tens of billions of light-years, enormous lattice of creation, drawn by gravity from a whisper of quantum noise. If you could float outside time and watch this structure evolve, you would see filaments tightening, clusters merging, and voids widening. as matter flows along the dark gravitational veins of the cosmos. In the far future, as dark energy continues to drive expansion, this cosmic web will begin to thin. Galaxies will be pulled away from one another faster than they can connect. Eventually, the web itself will dissolve into isolated islands of stars, separated by oceans of nothing. But for now, it is still forming. The web is alive, with motion, galaxies spinning, clusters merging, light bending through invisible valleys of mass. Every star, every planet, every atom in your body traces its lineage back through that web to the filament that birthed our galaxy, to the cold streams of dark matter that gathered hydrogen and lit the first suns. The universe is not chaos. It is a pattern written on a cosmic scale, a network vast beyond comprehension, yet governed by the same simple forces that bind atoms together. When we map the cosmic web, we are not merely tracing the shape of matter, we are mapping the shape of time itself, frozen in light, woven by gravity, illuminated by the faint, persistent glow of creation, the invisible architecture. The universe, you see the stars, nebulae, and galaxies glittering across the night, is only a faint shimmer on the surface of something far greater. Most of the matter in the cosmos cannot to be seen at all. It neither shines nor absorbs light. It reveals itself only through gravity's subtle pull. This unseen substance is called dark matter, and it is the invisible architecture upon which the entire universe is built. Our story with dark matter begins in the 1930 seconds with a Swiss astronomer named Fritz Zwicky. Studying the Coma cluster, a dense swarm of galaxies, he found that the galaxies were moving too fast to be held together by their visible mass. Something invisible, he concluded, must be, adding extra gravity Dunkelmaterie, as he called it in German. His calculations showed that there had to be at least 400 times more unseen mass than what the telescopes detected. Most of his colleagues dismissed the idea at the time, but Zwicky had glimpsed the first clue to one of cosmology's deepest mysteries. 4 decades later, Vera Rubin and Kent Ford provided the proof that changed everything. In the 1970 seconds, Rubin measured the rotation curves of spiral galaxies, plotting the speed of stars. At different distances from the center, according to Newtonian physics, stars farther from the center should orbit more slowly, much like planets in the solar system. But that wasn't what she found. The stars at the outer edges moved just as fast as those near the core. Something unseen was exerting gravitational pull, something extending far beyond the visible disk of stars. The mass of each galaxy was embedded in an enormous halo of dark matter, invisible but immense. Rubin's data made it clear. Most of the universe's matter was missing from view. Today, multiple lines of evidence confirm it. The cosmic microwave background, measured by WMAP and Planck, shows tiny temperature variations consistent with a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The gravitational lensing of distant galaxies, the way their light bends around massive clusters, matches models only if dark matter is included. The growth of cosmic structure, too, requires its presence. Without dark matter's early gravitational clumping, the universe would never have had time to form galaxies by now. We can even see dark matter's fingerprints in collisions. In 2006, astronomers studied the Bullet Cluster, two galaxy clusters that had passed through to each other. X-ray images showed hot gas, the ordinary matter, lagging behind, slowed by friction. But gravitational lensing revealed that most of the mass had sailed ahead untouched. The visible matter and the gravitational mass had separated. This was direct, visual evidence for dark matter as a real, distinct component of the cosmos. Yet, despite its gravitational dominance, dark matter remains invisible to every telescope. It does not emit, reflect, or absorb light. Whatever it is, it interacts only weakly, if at all, with ordinary matter. What could such a substance be? Physicists have proposed several candidates. The leading possibilities are WIMPs, weakly, interacting massive particles predicted by theories like supersymmetry. These hypothetical particles would have masses between 10 and 1,000 times that of a proton and would interact through the weak nuclear force. If they exist, trillions pass through your body every second, ghost-like and unnoticed. Experiments such as Look Zeppelin, Xenont, and Panda X, massive underground detectors, buried beneath mountains or deep in mines, are searching for the faintest flicker of their presence, hoping one might collide with an atom and leave a trace of light. So far, no confirmed detection has been made, but each experiment pushes the limits of sensitivity further. Another contender is the axion, a lightweight particle first proposed in the 1970 seconds to solve a problem in quantum chromodynamics. If axions exist, they could form a cold, diffuse field, permeating all of space. Experiments like ADMX, Axion Dark Matter Experiment, and Haystack are tuning ultra-sensitive radio cavities to catch their faint conversion into photons under magnetic fields. There are also more exotic possibilities. Sterile neutrinos, heavier cousins of the neutrinos we know could make up the dark matter. Or perhaps it is something entirely new, like superfluid dark matter, behaving more like a quantum condensate on cosmic scales. Other ideas modify gravity itself. Modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in 1983, suggests that Newton's laws change slightly at extremely low accelerations. Eliminating the need for dark matter, MOND can mimic galactic rotation curves, but struggles to explain cluster dynamics and the CMB. Most cosmologists therefore favour the particle hypothesis. In 2013, the Planck satellite provided the most precise measurements of the universe's composition. It showed that dark matter behaves as a cold, non-relativistic fluid, hence the name cold dark matter, CDM, and that this model, combined with dark energy, L, best fits all. Data. The result is the LCDM model, the current standard of cosmology. Still, mystery persists. If dark matter particles exist, why haven't we seen them? If they don't, what else could explain their gravitational effects? New clues may come from the cosmic web itself. Weak lensing surveys, like those from the Dark Energy Survey, DES and Euclid, map how light from distant galaxies is distorted by intervening mass. These distortions reveal the invisible distribution of dark matter across space and time. They show that dark matter formed the first filaments long before the first galaxies, and that it continues to guide the growth of cosmic structure even now. The scale of dark matter halos is astonishing. The halo enveloping the Milky Way extends over 200,000 light-years and outweighs all its stars by a factor of about 30. It is not uniform, it is rippled, clumped, and filled with subhalos that may host invisible dwarf galaxies. The Gaia satellite, mapping precise stellar motions, has found hints of such substructure, likely carved by ancient collisions with smaller halos. If we could see dark matter, the night sky would transform. Instead of stars, you would see enormous, faintly glowing spheres, vast halos overlapping like soap bubbles, connected by ghostly filaments stretching into the void. The stars would seem like dust motes floating in a vast, transparent ocean. Whatever dark matter is, it defines the architecture of reality. It sculpted galaxies, gathered the ingredients for stars and planets, and shaped the conditions that made life possible. Without it, the cosmos would be a featureless fog, no structure, no stars, no observers. The mystery of dark matter is not just about what the universe is made of, it's about how it built itself. Gravity alone could not have done this with visible matter alone. It needed a silent partner. Dark matter was that partner, the unseen hand that turned chaos into order, silence into structure, and energy into the galaxies we now call home. It remains one of the great unsolved puzzles of modern physics. Yet in that mystery lies possibility. The next particle discovered, the next detection made, could change not only our understanding of the cosmos but of matter itself. For now, we live in the glow of the visible, knowing that most of what is real is hidden, the force behind the great separation. In the late 20th century, cosmologists believed they were closing in on the universe's fate. Gravity, they thought, must eventually slow the cosmic expansion born in the Big Bang. The only question was, would it be enough to stop it entirely? To pull everything back into a final collapse, a big crunch? Or would the universe expand forever, gradually fading into cold silence? By the 1990 seconds, most expected the expansion to be slowing. The cosmos was ancient, its galaxies drifting apart, their mutual gravity locked in a cosmic tug-of-war. Measuring that, deceleration was supposed to be straightforward. Study the light of distant supernovae, stellar explosions so bright they can outshine entire galaxies and use them as cosmic mile markers. But when two independent teams, one led by Saul Perlmutter at Berkeley and another by Brian Schmidt and Adam Rees, looked into the deep sky in 1998, what they found changed cosmology forever. The expansion wasn't slowing down, it was speeding up. The discovery was as shocking as it was undeniable. The light from distant Type Ia supernovae was dimmer than expected, meaning those galaxies were farther away than gravity alone could explain. Something was driving them apart faster and faster. The universe was not winding down, it was accelerating. Whatever was causing this acceleration wasn't matter, it wasn't radiation, it wasn't anything we could see. To account for it, cosmologists resurrected a term once introduced and then abandoned by Einstein himself: the cosmological constant, symbolized by the Greek letter L. Lambda. Einstein had invented L in 1917 to stabilize a static universe, adding a repulsive energy to counter gravity. When Hubble later discovered cosmic expansion, Einstein called L his greatest blunder. Yet, decades later, it returned as the best explanation for an expanding universe that refuses to slow down. This repulsive component, this invisible energy woven into the fabric of space-time, is what we now call dark energy. Dark energy makes up about 68% of the total energy content of the universe, according to measurements from WMAP 2000 and 2010 and Planck 2013, 2018. Dark matter accounts for about 27%. The rest, everything we can see, touch, and measure directly, constitutes less than 5%. In other words, the entire luminous universe, all the galaxies, stars, planets, and life, is a crisis trace component. A small fraction of a cosmos dominated by the unseen. But what exactly is dark energy? One simple possibility is that it truly is the cosmological constant, a property of space itself. According to quantum field theory, even empty space is not empty. It seethes with virtual particles, fleeting fluctuations that appear and vanish in the quantum vacuum. These fluctuations contribute an intrinsic energy density to space. If this vacuum energy density is constant, it acts as a kind of uniform pressure, pushing the universe apart. However, there's a problem, an enormous one. When physicists calculate the energy of the quantum vacuum from known particle fields, the result is about 10 to the power of 120 times larger than the observed value of dark energy. This is the worst mismatch between theory and observation in all of science, known as the cosmological constant. Problem: it suggests that either our understanding of quantum vacuum energy is fundamentally wrong, or that an unknown mechanism cancels almost all of it out, leaving only a whisper. Because of this, many physicists have explored alternatives. One is quintessence, a slowly changing scalar field permeating all of space. Unlike the cosmological constant, which is fixed, quintessence can vary in time and space, altering the rate of expansion over cosmic history. Proposed by Ratra and Peebles in 1988 and further developed by Caldwell, Dave, and Steinhardt in 1998, quintessence acts like a dynamic form of dark energy whose strength evolves. Some versions predict that the acceleration could eventually slow or even reverse, leading to a new phase of cosmic contraction. Other theories propose more exotic possibilities. Phantom energy, for example, is a hypothetical form of dark energy with an equation of state less than -1. In this model, not only does expansion accelerate, it does so exponentially, tearing apart galaxies, stars, planets, and eventually atoms themselves in a catastrophic big rip. If phantom energy exists, the universe could end in roughly 22 billion years. There are also models that modify gravity itself instead of adding new energy, FR gravity. Brain-world cosmologies and massive gravity theories all attempt to explain cosmic acceleration through subtle changes to Einstein's general relativity. In sum, our universe is a brain floating in higher dimensions, where gravity leaks away, producing the illusion of acceleration. Others posit that gravity behaves differently on cosmic scales than it does locally, gradually weakening over distance. Each model carries its own predictions, but so far, observations best fit a simple cosmological constant L, that is, constant in time, perfectly uniform across space, and unchanging. Still, even that simplicity hides deep tension. The most striking evidence comes not just from supernovae, but from multiple independent observations. The cosmic microwave background reveals that the universe is geometrically flat, yet visible matter and dark matter together fall short of the critical density required for flatness. The missing energy density is exactly what dark energy provides. Baryon acoustic oscillations, BAO measurements, trace the imprint of ancient sound waves in the distribution of galaxies, matching an expansion history consistent with LEL. Large-scale structure surveys show that cosmic growth has slowed slightly, consistent, with an accelerating expansion that counteracts gravity. In 2011, the Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees for their a discovery of the accelerating universe, a discovery that redefined cosmology's foundation. And yet, the mystery deepens with every refinement. Recent observations show a tension between the Hubble constant H0, measured from the early universe via Planck, around 67.4 km SMPC, and the value inferred from local observations via Rees's SH0 project, around 73 km SMPC. If both are correct, it may mean that our understanding of cosmic expansion, and possibly of dark energy itself, is incomplete. Some cosmologists suspect a new form of energy or physics between recombination and the present a dark energy evolution or early dark energy phase that could reconcile the numbers. Dark energy is strange not just because of what it does, but because of when it appeared. For billions of years after the Big Bang, matter dominated. Galaxies formed, clusters coalesced, and gravity ruled. Then, about 5 billion years ago, dark energy began to dominate. The expansion rate, once slowing, started to accelerate. We live at precisely the cosmic moment when matter and dark energy are roughly equal, a fleeting balance in the universe's long history. Why now? Cosmologists call this the coincidence problem. Why should we exist in the tiny epoch when both components are comparable? In most of the universe's past, dark energy was negligible. In its future, matter will be diluted into irrelevance. Yet we find ourselves exactly at the turning point, as if watching the last breath of a slowing heartbeat before the cosmos drifts beyond our grasp. Dark energy doesn't just stretch space, it isolates it. As expansion accelerates, distant galaxies cross the cosmic event horizon, a boundary beyond which light emitted now will never reach us. Every billion years, more galaxies vanish from view, their light redshifted into oblivion. In about 100 billion years, even the nearest clusters, beyond the local group, will be gone from the sky. The universe will appear dark and empty to any distant future observer, its history erased by the very force that defines its destiny. This, perhaps, is dark energy's most haunting consequence. It not only drives the universe, apart, it conceals it from itself. It ensures that, in the far future, no intelligent beings will be able to deduce that an expanding universe ever existed. The cosmic web will fade, leaving only an island of stars adrift in a sea of invisible expansion. And yet, this invisible energy may hold the key to unifying the deepest laws of nature. Some physicists suspect that dark energy could be a clue to quantum gravity, the long-sought bridge between Einstein's relativity and quantum mechanics. If vacuum energy truly drives cosmic acceleration, Then, understanding its origin could reveal how space-time itself emerges. From quantum fields, a question at the heart of modern theoretical physics. Others see dark energy as the signature of the universe's geometry, the curvature of higher dimensions projected into our four-dimensional view. Theories like the holographic principle proposed by Uft and Susskind suggest that all the information in our universe might be encoded on a distant cosmic boundary, an event horizon of sorts. In that framework, dark energy could reflect the information density of that horizon itself. Whatever its nature, dark energy defines the future of everything. If it remains constant, expansion will continue forever, galaxies receding into a cold, black silence, the big freeze. If it strengthens, the universe will end in a big rip. If it weakens, expansion might slow and reverse, leading to a cosmic rebirth. Every atom, every star, every photon is caught in that uncertain tide. We name it dark not because it is evil or cold, but because it is hidden. We cannot see it, touch it, or test it directly. We can only watch what it does to the galaxies, to the light, to the geometry of space-time itself. It is not merely an energy, it is the invisible will of the cosmos, sculpting the ultimate shape of eternity. And though we do not yet know its nature, we know this: it is real. It stretches the universe. Around us, even now, every moment you live, the space between galaxies grows wider, the fabric of the cosmos thinner. The same expansion that began in the first instant of time continues through you, through every molecule, every breath, every heartbeat. Dark energy is not elsewhere, it is here. It is in the distance between galaxies and in the silence between stars. It is the measure of time itself stretching toward infinity, carrying the universe outward on an endless journey into the dark. Cosmic time machines. The deeper we look into the universe, the more we see that space and time are not separate things at all. They are woven together into a single entity, space-time. And this fabric, flexible and dynamic, is the stage upon which all of reality unfolds. Einstein's general theory of relativity, published in 1915, was not merely a new law of gravity, it was a new conception of existence. In it, gravity is not a force acting at a distance, as Newton imagined, but the curvature of space-time caused by mass and energy. Matter tells space-time how to curve. Curved space-time tells matter how to move. This simple idea changed everything. It explained why planets follow elliptical orbits, why starlight bends around the sun, why time slows near massive objects. But it also opened doors to some of the most astonishing possibilities in physics: wormholes, black holes, and time dilation pathways and paradoxes, where geometry itself becomes destiny. When Einstein's equations were first solved by Karl Schwarzschild in 1916, they revealed something extraordinary. For a massive object compressed into a small enough volume, space-time curves so extremely that light itself cannot escape. This was the first exact description of what we now call a black hole. Within its event horizon, all paths through space-time, even light lead inward, never outward. To an outside observer, a falling object appears to slow as it approaches the horizon, its light red-shifting into invisibility. To the object itself, nothing special happens. It crosses the horizon and falls inevitably toward the singularity, a point where curvature becomes infinite and the known laws of physics collapse. Yet, In that very collapse lies a window into something deeper. At the singularity, space-time is no longer continuous. Quantum effects dominate. Time and space lose their meaning. To describe this region, we need a quantum theory of gravity, one that unifies the smooth geometry of relativity with the granular probabilities of quantum mechanics. Such a theory does not yet exist, but it is here, inside black holes, that we know it must be born. Black holes are not merely objects, they are laboratories of cosmic geometry. They show us that space-time can be shaped, stretched, and even folded. In 1935, Einstein and Nathan Rosen explored a curious feature of the Schwarzschild solution, a mathematical bridge connecting two separate regions of space-time. They called it an Einstein-Rosen bridge, what we now call a wormhole. In principle, a wormhole could link distant parts of the same universe, or even two different universes, through a hidden tunnel outside normal space. The idea has fascinated physicists and storytellers alike, but Einstein-Rosen bridges, as originally conceived, are not traversable. They pinch off too quickly, closing before light or matter could pass through. For decades, wormholes remained a mathematical curiosity, possible on paper, impossible in practice. That changed in 1988, when Kip Thorne and Michael Morris published a paper describing traversable wormholes solutions to Einstein's equations that could, in theory, remain open if threaded with a form of exotic matter possessing negative energy density. Such matter would violate the ordinary energy conditions of general relativity, but it is not forbidden by quantum physics. The Casimir effect, in which vacuum fluctuations between metal plates produce negative energy, offers a hint that nature allows such states, albeit fleetingly. In these models, a wormhole acts like a shortcut through space-time. You could enter one mouth, travel a short distance locally, and emerge from the other mouth light years away. The geometry is not unlike folding a sheet of paper so that two distant points touch, then punching a hole through. The journey doesn't exceed the speed of light. You simply take a shorter path through curved space. If such structures exist and if they could be stabilized, they would be true cosmic time machines. Move one mouth of the wormhole near a massive object where time runs slower, and then bring it back. The two ends would become desynchronized in time. Step through one mouth, and you could, in principle, emerge in the past. This is not science fiction. It is an implication of relativity itself. But every attempt to use relativity to engineer a time machine runs into paradoxes. Grandfather paradox, closed time-like curves, violations of causality. The universe seems to guard its timeline carefully. Physicist Stephen Hawking proposed the chronology protection, conjecture the idea that quantum effects would destroy any time machine before it could operate, preserving causality at all costs. Still, the mathematics remains open-ended. Einstein's equations do not explicitly forbid wormholes or time loops. They only demand extreme conditions, massive energy densities, negative pressures, quantum fields behaving in ways we do not yet understand. The universe might already contain such phenomena, hidden behind horizons or buried in the geometry of inflation. Even without wormholes, relativity reshapes our understanding of time itself. Time is not universal. It flows differently for everyone, depending on speed and gravity. This is time dilation, confirmed by countless experiments. Clocks aboard satellites in orbit tick slightly faster than those on Earth, because gravity here is stronger. Without correcting for this effect, GPS systems would drift by kilometers each day. Near a black hole, the effect becomes extreme. A minute near the horizon could equal years far away, a scenario captured vividly by nature itself. The supermassive black hole, Sagittarius A*, at the center of our galaxy, warps time by measurable amounts, even tens of thousands of kilometers from its surface. At cosmic scales, time dilation plays another role. It shapes what we see when we look outward. The light from distant galaxies, stretched by expansion, carries a record of slower clocks and longer seconds. The universe's history is not uniform. It unfolds at different rates in different regions, stitched together by light across billions of years. Einstein's insight that time and space are elastic remains one of the most profound in science. It means that the structure of the universe is not fixed. It can twist, stretch, ripple, and fold. We have seen it ripple directly in gravitational waves, first detected in 2015 by the LIGO collaboration. Two black holes, merging more than 1 billion light-years away, sent tremors through the fabric of space-time itself. Those waves passed through Earth, subtly stretching and compressing us by less than a fraction of a proton's width. Proof that space and time are not static, but alive with motion. Relativity also permits cosmic strings and domain walls, hypothetical relics from the early universe that could warp space-time around them. If they exist, a cosmic string could act as a gravitational lens with distinctive double images, a reminder that even the emptiest vacuum may be full of geometry waiting to be revealed. But perhaps the most profound implication of relativity is that it erases the distinction between past, present, and future. In Minkowski's four-dimensional space-time, all moments coexist. The universe is a vast, static, manifold, a block universe where time is simply another dimension, like space. We do not move through time. Rather, we are extended within it. The illusion of now may be the way consciousness slices that continuum into experience. This idea leads to strange but testable consequences. If space-time is a fixed geometry, then causality, the flow of cause and effect, is emergent, not fundamental. Quantum mechanics may encode all possible histories, while relativity arranges them into a coherent whole. Some physicists, like Julian Barber, suggest that time may not exist as a separate entity at all, only relations between configurations of the universe. At the far edge of theory, relativity meets quantum gravity. In loop quantum gravity, space-time is composed of tiny discrete loops of area and volume woven together into a spin network. In string theory, all of space-time arises from the vibrations of one-dimensional strings in higher dimensional space. In both views, geometry is not fundamental, it is emergent, built from more elementary information. This idea reaches its boldest form in the holographic principle, proposed by Gerard Hooft and developed by Leonard Susskind in the 1990 seconds. It suggests that all the information contained in a region of space is encoded on its boundary, just as a hologram encodes a three-dimensional image on a two-dimensional surface. The principle gained support through Juan Maldacena's AD-S-CFT correspondence in 1997, which showed that a theory of gravity in a curved space could be mathematically equivalent to a quantum field theory on its boundary with no gravity at all. If true, This means that our universe could be a projection, a three-dimensional shadow of quantum information written on a distant cosmic horizon. In such a picture, space-time itself, with its curves, wormholes, and gravitational waves, might emerge from entanglement, the fundamental connectivity of quantum states. Some researchers have even proposed that ER equals EPR, that Einstein-Rosen bridges ER, quantum entanglement, EPR, are two sides of the same coin. Every pair of entangled particles might be connected by a microscopic wormhole, knitting space-time together from the fabric of quantum information. In this way, wormholes are not just shortcuts, they are the threads of reality itself. When you look up at the night sky, you are not looking across an empty void. You are seeing the geometry of space-time stretched between you and the stars. Every photon's path is a curve through that geometry. Every second of your life is a trajectory through its depths. You are not in the universe, you are part of its structure, tracing your own geodesic through the same fabric that carries galaxies and light. Relativity teaches us that the cosmos has no absolute here, no universal now, no single map that everyone shares. Every observer draws their own coordinates, their own version of reality, consistent but incomplete. And yet, together, these frames weave a coherent whole, a living, four-dimensional tapestry that is the universe itself. In the end, geometry is not only the shape of space, it is the logic of existence. Gravity, time, and motion are all expressions of that geometry, the universe's silent language. Wormholes, black holes, expansion, all of them are how space-time speaks to itself. And in its language, there is no edge, only curvature, no boundaries, only horizons. The universe does not sit in space, it is space, folding endlessly into its own infinity. Signals from the deep. The universe is not silent. Across the cosmic dark, it hums, glows, and vibrates with information. Every star, every black, a hole, every collision or burst of light sends a signal, a messenger traveling across space and time to tell its story. For billions of years, these signals have crossed the vacuum, and now, on a small blue world orbiting a modest star, we have learned to listen. Our first ears were simple: eyes, then lenses, then mirrors. In 1609, Galileo Galilei pointed a small telescope toward the heavens and saw the roughness of the moon, the moons of Jupiter, and the stars that make up the Milky Way. In that moment, astronomy changed from poetry to physics. Yet Galileo's telescope collected only visible light, a narrow slice of the electromagnetic spectrum, spanning wavelengths from about 400 to 700 nanometers. For centuries, that narrow window was all we could see. But the cosmos speaks in many tongues. It radiates not just visible light, but radio waves, infrared heat, ultraviolet light, X-rays, and gamma rays, an orchestra spanning wavelengths from kilometers to trillionths of a meter. Each wavelength carries different information about the same universe, revealing layers invisible to the human eye. In 1931, an engineer named Carl Jansky detected a mysterious hiss of radio static coming from the center of the Milky Way. His discovery marked the birth of radio astronomy, opening a window into a universe alive with invisible light. Later, in the 1950 seconds, Grote-Reber built massive parabolic dishes to map the radio sky, discovering strange sources, quasars and pulsars that emitted energy millions of times greater than stars. Radio waves showed us the cold, molecular skeleton of the cosmos, the vast clouds of hydrogen that stretch between stars and galaxies. Infrared telescopes revealed the warmth of newborn stars still hidden within their dust cocoons. X-ray and gamma-ray observatories exposed the violence of black holes, neutron stars, supernovae. The universe, it turned out, is not serene, it is active, turbulent, and profoundly alive. Each band of the spectrum required new technology. In 1962, Riccardo Giacconi launched the first X-ray detector aboard a rocket, discovering Scorpius X1, the brightest X-ray source in the sky. From that beginning grew a fleet of space. Telescopes Chandra, XMM Newton, and NuSTAR, each designed to capture energy that Earth's atmosphere blocks. In the infrared, satellites like IRIS 1000, 983, Spitzer 2003, and the James Webb Space Telescope 2021 have mapped the hidden universe, dust-shrouded galaxies from the early six, cosmic dawn, planets glowing with the faint heat of formation and the delicate chemistry of life's building blocks in interstellar clouds. In the visible and ultraviolet, the Hubble Space Telescope, launched in 1990, has shown us galaxies 13 billion years old, its mirror catching photons that left their sources before Earth existed. In the ultraviolet, GALEX and HST's COSE instrument have traced the ionized filaments connecting galaxies, the cosmic web itself, illuminated by ultraviolet light from distant quasars. But light is only one kind of signal. The universe speaks in other messengers too. In 2015, a century after Einstein's prediction, we finally heard the universe tremble. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the faint ripple of time, space-time from the merger of two black holes more than 1 billion light-years away. The signal, lasting just 0.2 seconds, matched the predictions of general relativity with breathtaking precision. Each black hole weighed about 30 solar masses. When they collided, they converted roughly 3 suns' worth of mass into pure gravitational energy waves that stretched and compressed Earth by less than 1,000th of a proton's width. This was the beginning of gravitational wave astronomy, the newest way of listening to the universe. Unlike light, gravitational waves pass unhindered through matter. They carry information directly from the darkest, most hidden regions of space-time, places light can never escape. Since that first detection, LIGO, Virgo, and CAGRA have recorded dozens more signals. Black holes colliding, neutron stars merging, cosmic cataclysms echoing across the void. Each event adds a new voice to the cosmic chorus. In 2017, when 2 neutron stars collided in a galaxy 130 million light-years away, astronomers observed it both in gravitational waves and in light, a true multi-messenger event. It produced gold, platinum, and other heavy elements, and it confirmed that such mergers are the cosmic forges where many of Earth's rarest elements are born. To hear these faint signals, humanity has built instruments of extraordinary precision. LIGO's twin observatories in Louisiana and Washington use laser interferometry to measure changes in distance smaller than 1/10,000th of a proton's diameter over a 4-kilometer arm length. Future detectors like LISA, the Laser Interferometer Space Antenna, set for launch in the 2032, will place 3 spacecraft millions of kilometers apart, forming an equilateral triangle orbiting the Sunday LISA will listen for lower frequency waves. The slow dances of supermassive black holes the whispers of cosmic strings, and perhaps even the gravitational waves left over from the Big Bang itself. These technologies have transformed astronomy from a discipline of light to a symphony of signals. Today, astronomers combine light, particles, and gravity to build a multi-messenger picture of the cosmos. When a supernova erupts, we can detect its optical flash, its X-rays, its neutrino burst, and even its gravitational ripple. Each messenger tells a different story, and together they compose a fuller truth. Neutrinos, nearly massless particles first predicted by Wolfgang Pauli in 1930, are among the universe's most elusive signals. Produced in vast numbers in nuclear reactions, inside stars, and during supernovae, they can pass through entire planets without interacting. In 1987, the 1987 Kamiokande II and IMB detectors in Japan and the United States captured a handful of neutrinos from supernova 1987A, the first time humanity directly observed the internal collapse of a star. Today, detectors like IceCube, buried beneath the ice of Antarctica, monitor a cubic kilometer of frozen darkness for faint flashes of light triggered by neutrino collisions. IceCube has already traced ultra-high energy neutrinos to distant blazars, supermassive black holes, beaming jets of radiation across the universe. These ghostly particles, born in the most violent accelerators nature can make, tell us about physics far beyond the reach of any laboratory on Earth. And then there are the cosmic rays, high-energy protons, and atomic nuclei that strike Earth's atmosphere from space, discovered by Victor Hess in 1912. They, too, are messengers, accelerated by supernova remnants, pulsars, and perhaps even active galactic nuclei. Their energies exceed anything produced by human technology, some reaching 10 to the power of 20 electron volts. To study them, arrays like the Pierre Auger Observatory in Argentina cover thousands of square kilometers, watching for the faint blue glow of air showers triggered by these interstellar bullets. All these signals, light, gravity, neutrinos, particles, form the language of the cosmos. Each one has traveled across space and time, carrying with it information about where it came from, what it encountered, and how the universe has changed along the way. The distances are staggering. Light from the Andromeda Galaxy takes 2.5 million years to reach. Thus, the cosmic microwave background photons have been traveling for 13.8 billion years. Some neutrinos from distant supernovae may cross billions of light years, unimpeded by anything, to arrive at our detectors as silent ambassadors from the past. When we detect them, we are not just observing distant events, we are receiving messages from the dawn of time. Our instruments are evolving to match the vastness of the task. The Vera C. Rubin Observatory, under construction in Chile, will soon begin the legacy survey of space and time. LSST, a decade-long project to image the entire southern sky every few nights, mapping billions of galaxies and transient events. The Square Kilometre Array, SKA, under development in Australia and South Africa, will be the largest radio telescope ever built, capable of detecting the faint hydrogen signal from the cosmic dark ages before the first stars ignited. The Nancy Grace Roman Space Telescope, launching in the late 2022, will combine wide-field imaging with infrared sensitivity, tracing dark energy's imprint on cosmic structure. Together, These observatories will turn the universe into a living laboratory, a place we no longer simply observe, but continuously monitor, listening to every frequency, every messenger, every vibration. Each detection deepens our understanding, but also humbles it. The universe's signals are faint and ancient. They have crossed expanding space, redshifted, scattered, and stretched. Many are lost forever, absorbed by dust, bent by gravity, or diluted by time. What reaches us is a whisper, and from that whisper we reconstruct the symphony. Astronomy, at its core, is an act of translation, from light into numbers, from numbers into meaning, from meaning into wonder. The signals we receive are not just data, they are the universe remembering itself. It is humbling to realize that some of the light reaching Earth tonight began its journey before our sun was born. It has traveled through epochs of cosmic evolution, through eras of star birth and death, through the forming of galaxies, through the long expansion of space. When it finally touches a detector or an astronomer's retina, the universe completes a story billions of years in the making, and we, fragile creatures made of atoms forged in old stars, have built the means to hear it. We have turned mountains into mirrors, deserts into radio arrays, oceans of ice into detectors. We have sent telescopes beyond the atmosphere, into orbits 1,000,000 miles from Earth, to catch the faintest photons from the beginning of time. Every signal that arrives is a form of contact, not with aliens or civilizations, but with the cosmos itself. When you look at an image from Hubble or listen to a gravitational wave converted into sound, you are hearing the voice of the universe speaking across time. It speaks in radiation, in vibration, in silence. And through the instruments we've built, that voice now has an audience. We are the sense organs of the cosmos, the means by which the universe becomes aware of its own vastness. To listen to the deep is to participate in its unfolding story. Every photon caught, every wave measured, every data point recorded brings the universe closer to knowing itself. The stars are not silent after all they have been singing since the beginning. And now, finally, we are learning the tune, singularities, quantum foam, and the Planck frontier. Every law of nature has a domain where it works beautifully and a boundary where it fails. Deeper we've looked into the structure of the universe, the more we've realized that even our most fundamental theories, general relativity and quantum mechanics, are incomplete. Each describes reality perfectly within its realm. Relativity for the cosmic, quantum theory for the microscopic. But at their intersection, where gravity is strong and space is small, they contradict each other. That boundary, the place where physics itself fractures, is known as the Planck frontier. The Planck scales are the natural limits set by the constants of nature. The speed of light, k, Planck's constant, r, which governs quantum behavior, and Newton's gravitational constant, g, which sets the strength of gravity. From these three, physicist Max Planck derived units that define the smallest possible scales of space and time where classical concepts lose meaning. The Planck length is about 1.616 times 10 to the power of negative 35 meters, 100 million trillion times smaller than a proton. The Planck time, the time it takes light to cross that length, is 5.39 times 10 to the power of negative 44 seconds. Below these scales, space-time itself is thought to dissolve into a turbulent quantum froth, a quantum foam, as John Wheeler called it. Here, the smooth geometry of Einstein's relativity ceases to apply. Space and time no longer behave as continuous dimensions, but as fluctuating, probabilistic entities. Imagine the surface of an ocean, but seen up close, each wave crest breaking into smaller ripples, each ripple into spray, until the very notion of surface disappears. That is space-time at the Planck scale, not a fabric, but a storm. We know such a regime must exist because of singularities, places where relativity predicts infinite density and curvature. Black holes and the Big Bang both contain them. In each case, the equations that describe space-time return nonsensical results. Physicists do not believe infinity is physical. Rather, it signals that our current framework is inadequate. Somewhere below the Planck scale, a new theory must take over a quantum theory of gravity. Over the past century, humanity has built two towering pillars of physics: general relativity, describing gravity as geometry, and quantum mechanics, describing matter and energy as probabilities. Each has been tested to extraordinary precision. Relativity predicts the orbit of Mercury, the bending of light by gravity, the timing of pulsars, and the expansion of the universe, all correct, to many decimal places. Quantum mechanics predicts atomic spectra, semiconductor behavior, and nuclear decay with equal success. Yet, when we try to unite them, the math breaks down. The curvature of space-time resists quantization. Gravity does not fit naturally into the probabilistic framework that governs particles. To bridge that divide, physicists have proposed several approaches. One is string theory, developed beginning in the 1970 seconds by researchers including Leonard Susskind, John Schwartz, and Michael Green. In string theory, the fundamental building blocks of reality are not point-like particles, but one-dimensional strings vibrating at different frequencies. Each vibration corresponds to a particle, an electron, a quark, a photon, and one particular vibration corresponds to the graviton, the hypothetical quantum of gravity. String theory's elegance lies in how it automatically includes gravity and unifies all forces within a consistent quantum framework. But it comes at a cost. It requires extra dimensions, usually 10 or 11 inches total, curled up into shapes known as Calabi-Yau manifolds. These dimensions are too small to detect, but their geometry determines the properties of the universe we observe. Another approach is loop quantum gravity, LQG, pioneered by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli. LQG starts not with particles but with space itself, quantizing its geometry. In this view, space is made of discrete loops, forming a spin network, a web of quantum geometry that replaces continuous space-time. Volumes and areas become quantized. There are smallest possible units of space, just as energy is quantized in atoms. Both theories, despite their differences, point toward the same idea. At the Planck scale, space and time are not fundamental, they emerge from something deeper. We catch glimpses of this frontier in the physics of black holes. A black hole, by definition, is a region where gravity has become so strong that nothing, not even light, can escape. According to relativity, its boundary, the event horizon, is the ultimate one-way surface. Yet in 1974, Stephen Hawking discovered that black holes are not entirely black. Quantum effects at the horizon cause them to emit radiation, a phenomenon now known as Hawking radiation. Over immense timescales, black holes can evaporate, converting their mass into energy. This creates a paradox. If black holes evaporate completely, what happens to the information about what fell in? Quantum mechanics insists that information cannot be destroyed. Relativity seems to say it can. This is the black hole information paradox, one of the greatest puzzles in modern physics. In the 1990 seconds, Leonard Susskind and Gerard Hooft proposed a resolution. The information is not lost, it is encoded on the surface of the horizon in tiny quantum fluctuations. This insight led to the holographic principle, suggesting that the three-dimensional contents of a region can be described by data on its two-dimensional boundary. Later, Juan Maldacena's AD-CFT correspondence 1997 gave this idea mathematical form, linking gravity in a curved space to a quantum field theory without gravity on its edge. The holographic principle has since become one of the cornerstones of quantum gravity research. The same principle may apply to the entire universe. The cosmological horizon, the boundary of what we can observe, may encode all the information inside it. The total entropy of the observable universe, calculated using the Bekenstein-Hawking formula, is roughly 10 to the power of 122 kb, corresponding to the area of its horizon in Planck units. This suggests that the universe, too, might be holographic, a projection of quantum information from its boundary. In this sense, the Planck frontier is not merely a limit of scale, it is the interface between reality and information, between geometry and computation. At that boundary, space-time may behave, less like a smooth continuum and more like a digital code. Bits of information woven into the liturgy, fabric of existence. Some physicists, like Seth Lloyd and Jacob Bekenstein, have suggested that the universe itself can be thought of as a quantum computer, one that has been processing information since the Big Bang. The total number of operations it could have performed since that moment is roughly 10 to the power of 120, coincidentally close to the number of particles in the observable universe. But our understanding of this realm is still fragmentary. The Planck scale is far beyond experimental reach. Even the most energetic particle collisions at the Large Hadron Collider, reaching energies of 13 tera-electron volts, probe distances around 10 to the power of negative 19 meters, still 16 orders of magnitude larger than the Planck length. To reach that frontier directly, we would need energies of 10 to the power of 19 GeV, 1 billion trillion times greater than anything we can produce. Yet the universe itself once reached those energies. In the first 10 to the power of negative 43 seconds after the Big Bang, the Planck epoch, gravity, electromagnetism, and the nuclear forces were one. The temperature was about 10 to the power of 32 Kelvin. The density was near 5 times 10 to the power of 96 kilograms per cubic meter. Every known law of physics breaks down under such conditions. That first instant is beyond simulation, beyond experiment, yet its echoes may still be measurable in the cosmic microwave background or in the faint spectrum of gravitational waves. From the birth of the universe, some speculative models try to peek beyond the singularity. In loop quantum cosmology, the Big Bang is replaced by a big bounce, a transition from a previous contracting universe to our current expanding one. At high densities, quantum gravity creates a repulsive force that prevents true singularities, causing the universe to rebound instead of collapse. Similarly, in certain versions of string cosmology, the Big Bang is the result of colliding branes in higher dimensional space, as in the ekpyrotic model proposed by Steinhardt and Turok. Other theories propose a cyclic or self-replicating universe, where each collapse births a new expansion, and the process continues indefinitely. In each cycle, the laws of physics could reset or evolve like new software running on the same underlying code. But all of these ideas face the same fundamental question: what is space-time made of? If it is quantized, what are its atoms? If it is emergent, what gives rise to it? Is it information, energy, topology, or something beyond our current language? At the Planck frontier, words like before, after, here, and there lose their meaning. Causality, locality, and continuity, the foundations of physics, begin to blur. The very notion of inside and outside dissolves when space-time itself is in flux. The quantum foam is not. Somewhere within the universe, it is the universe at its most fundamental level. To visualize it is almost impossible. At one moment, a tiny bubble of space-time appears, fluctuates, and vanishes. Another forms, joins with others, and merges into larger structures. The foam boils endlessly, creating and annihilating pockets of curvature, micro wormholes, and quantum tunnels. Out of this chaotic in-sea, larger patterns stabilize regions that smooth out into the continuous space-time we inhabit. Our universe, in this view, is one such region, a calm eddy in the storm of existence. One day, we may find experimental hints of this structure. The Planck satellite's measurements of the cosmic microwave background have already tested inflationary models down to 1 part. In 10 to the power of 5, searching for the subtle B-mode polarization patterns that would reveal primordial gravitational waves, ripples from quantum fluctuations stretched across the early universe. Future missions like CMBS-4, Lightbird, and LISA may yet detect these signatures, giving us the first indirect glimpse of the Planck frontier. Until then, we can only approach it through mathematics and imagination. The Planck scale is where our equations fail and where new ones must arise. It is the event horizon of understanding, a mirror that reflects our limits. But that boundary is not a defeat, it is an invitation. Every breakthrough in physics, from Newton to Einstein, from Bohr to Feynman, came from confronting failure. The points where our theories break are where the next revolutions begin. At the Planck frontier, we glimpse not the end of science, but its renewal. It is the silence before the next discovery, the edge of language where new concepts will one day take shape. There, in the froth of quantum space-time, perhaps the universe is still being written bit by bit, loop by loop, vibration by vibration. And when we finally understand that code, we will not just know how the cosmos began, we will know what it means for anything to begin at all. The edge of understanding. At every frontier of knowledge, physics encounters not just new facts, but new questions about what it means to know. The further we push into the dark, the more we find that understanding the universe is inseparable from understanding ourselves, our methods, our limits, our place in the cosmic story. Science begins in measurement. We observe, we quantify, we compare. But beyond the data, beyond the constants and equations, lies a question older than science itself. Why does the universe exist at all? Physics tells us how it maps the processes, the evolution, the interactions, but the why lingers like an echo just beyond our reach. This is not mysticism. It is humility before reality. The same equations that predict planetary motion and the birth of stars also lead us to singularities, infinities, and paradoxes regions where mathematics, so precise elsewhere, breaks apart. At those points, the universe becomes its own riddle. Relativity tells us that space and time are flexible. Quantum theory tells us that certainty is an illusion. The two pillars of modern physics, so powerful individually, are incomplete together. Their marriage, the long-sought theory of everything, remains elusive. It is not just a missing formula, it is a missing understanding of what the universe truly is. At the smallest scales, quantum mechanics describes particles as waves of probability. Existence itself becomes statistical. At the largest scales, general relativity treats the cosmos as a smooth, deterministic fabric. When we try to merge them, the result is mathematical chaos. Equations explode into infinities. Time and space dissolve into uncertainty. This clash is not a failure of science, it is the discovery of its next horizon. Each theory holds a piece of truth, and where they overlap, we glimpse something deeper. A universe that may not be a thing at all, but a process, self-organizing, emergent, and relational. Perhaps reality is not made of matter or energy, but of information. This is the view emerging from quantum information theory, which treats the universe as a vast computation, bits of existence flipping through physical laws. John Archibald Wheeler summarized it in 3 words: it from bit. The idea is simple but profound. What we call matter may be the manifestation of information at play. Every particle, every field, every moment of time may be an expression of data, structured by physical law. At this level, the universe begins to resemble consciousness itself, a network of relationships that exist only through interaction. Observation is not passive, it shapes reality. The act of measurement in quantum mechanics collapses possibilities into outcomes. This does not mean the mind creates the universe, but it reminds us that participation is fundamental. We are not outside observers looking in. We are part of the system we're trying to understand. Physics, when pushed far enough, begins to speak the language of philosophy. Questions of existence, causality, and perception cease to be abstract. They become experiments. If the universe began with the Big Bang, what came before? If time has a beginning, can it have an end? If the universe is infinite, what does beyond mean? Each of these questions blurs the line between physics and metaphysics, not because we abandon reason, but because reason leads us there. Consider the anthropic principle, first articulated by Brandon Carter in 1973. The universe must be compatible with the existence of observers like us, because we are here to observe it. At first, it sounds tautological, but its implications run deep. Why are the constants of physics, the strength of gravity, the charge of the electron, the speed of light so precisely balanced that atoms, stars, and life can exist at all? Change any of them slightly, and the universe would be sterile. Is this fine-tuning a coincidence, a necessity, or evidence of a deeper multiverse where all combinations exist and only some produce minds to notice them? Philosophy has always hovered at the edge of cosmology. The ancient Greeks imagined a cosmos without beginning. Medieval thinkers argued for creation from nothing. Modern cosmology, with its expanding universe and quantum fields, revives those same debates under new names: eternal inflation, vacuum fluctuations, cyclic models. Each theory seeks not just a mechanism, but a metaphysical answer, a way to reconcile the universe's existence with logic itself. Even the question of nothing is no longer simple. In quantum field theory, the vacuum is not empty. It seethes with virtual particles flickering in and out of being, a storm of potentiality from which energy can emerge. The Casimir effect, measured in the 1,940 seconds, proves that even empty space exerts pressure. So if the universe did arise from nothing, it was a quantum nothing, a sea of probabilities, pregnant with everything that would ever exist. Physics, it seems, is turning into a mirror. The more we understand the universe, the more it reflects our own structure of thought. The cosmic microwave background is a kind of memory, the universe remembering itself 13.8 billion years later. Our telescopes are extensions of the senses, our equations extensions of reason. When we map the stars, we are charting not only space, but the reach of human curiosity. There is an old philosophical question: does the universe require an observer to exist? Most physicists would say no, the cosmos existed long before life appeared. And yet, it is only through consciousness that the universe becomes aware of itself. Every photon that strikes an eye, every equation that captures a law, is part of the same process. Reality examining itself from within. Perhaps this is what it means for the universe to have no edge. Not just spatially, but conceptually. There is no final boundary between the known and the unknown, only the next question, waiting beyond the horizon of understanding. In that sense, the edge of the universe is not where space ends, but where thought begins. The boundary of physics is not the end of science, it is its continuation into reflection, imagination, and wonder. And when physics meets philosophy, what emerges is not contradiction, but a deeper unity, the realization that the quest to know the universe is also the quest to know ourselves. We are not at the center of the cosmos, but we are at the center of its meaning. The universe has been expanding for 13.8 billion years, forming stars, galaxies, and the elements of life. And in one corner of that vastness, it has produced beings capable of asking why. That question, the one that will never be answered completely, is the true edge of the universe. Not a place, but a pursuit. Not an end, but a horizon that moves forever as we approach. And as long as there are minds to wonder, the cosmos will never stop expanding.